Okay, this is video 2 in the first lesson of sound. So we just talked about how sound is a longitudinal mechanical wave that travels through matter. That's why it's called mechanical. So the reason that we say it travels away from the object, this is mostly if you imagine like once again a pebble dropped into a pond. It's not just one direction that it's going. It's kind of going out in all directions. And I think if you're looking at it from the top, it kind of does. It mimics pretty well what sound would look like if you could see it. You could probably see sound or the effects of it if you had like say sand on a drum. If you've ever seen something like that, and you're hitting it, you can actually see the waves as they push along the matter because of how it affects the matter that's there. In the case of air, you don't see air stretching. So, when we say it's a longitudinal wave, the wavelength itself would be from point to point wherever it's similar, from either the very beginning of the compression zone or the end of the compression zone to the beginning of the compression zone to the end of the compression zone. In any case, you'd have to be from the front to front, back to back, middle of the rarefaction to the other rarefaction. Just basically wherever its similar starting point is, that's what a wavelength would be for sound. Now, if you think which one would be longer, a sound wave or a radio wave, or a light wave, sound waves are much longer than almost all light waves, except for the really long ones like radio waves, the longest of radio waves even, at the very, very, very bottom of the spectrum. So sound waves are pretty long waves. And if you remember last time, we talked about longer waves having different properties like bendiness and all that kind of stuff. We're going to get into that a little bit more next lesson. But for now, it's enough to say that it's a longitudinal wave, which means it's going to have compressions of matter and stretches out. Just like if you're thinking about a rubber band, if you were to stretch it out or compress it in one spot, right, pull more into one spot than another, it would have to come from the other area, because the matter doesn't just disappear or appear in one spot or another. It's coming from somebody. Where that's why you have these rarefactions, which are the stretch out zones, and the compression zones. Really, inside of these compressions, there's a lot of more pressure too. I know we don't talk about it that much, but sometimes sound waves are called pressure waves even. So when we say it's going through a medium, just for a quick refresher here, this key vocab term, a medium is a substance through which a wave can travel. So say there's a disturbance on this side of the solid right now. These solid molecules, basically molecules that are arranged close together in a locked form, whether that's like, let's think about this like water once again. Say this is ice. If you were to knock into the ice on one side of it, these molecules would pretty quickly hit against these ones and hit against these ones and these ones and these ones and so on and so forth. These would push against these to create compressions, and on the other side, whatever it's touching, it will compress that. So more often than not, you have ice in a liquid like water, right? So these molecules would end up bumping into the liquid molecules around it, or the molecules in the liquid form. And then say the molecules of the liquid in a glass of water that has ice in it would touch up against the gas at the top of the glass. So, even if you were tapping on the ice cube somehow in the glass, that sound could still travel into the air. But along the process of that, when it moves from one medium to another, you definitely have a loss in energy. Or not a loss in energy, but a dissipation. It just doesn't seem to all go in that same direction. It's not very efficient. So that's why a lot of times you can scream underwater, but a lot of that sound energy that's going through the water isn't going to travel up to the surface of it. It'll just get trapped in the water itself. So the molecules are being pressed together as the sound waves move through matter. Longitudinal waves travel through the springs, just like sound waves travel through air. So if we were using a slinky, if you have a slinky at home, you could push it, and you'd watch this little tiny slug of energy going through here, this pressure zone called a compression zone. And it would move in one direction, but in air, it just travels in all directions because there's not really slinkies in air. It's just a whole bunch of molecules that are out there ready to be hit like dominoes. This is a great video, and I want you to pause right now and do two things. One, in your guided notes, you should try to answer the following here, and then I'd like you to watch the video. You can watch that video by going into the slides from the weekly update that were posted on there, and just go ahead and watch it. It's about 5 minutes long, I think, and it was really nice. Okay, so now I'm expecting you to just come back from watching that video. The idea that the medium can affect the rate of sound travel is really important for sound, and understanding why basically it's not just for sound but in general for waves. Mediums will always affect a wave. Even light, which doesn't need a medium to travel through, is affected by mediums. And it's important to know that sound and light act in opposites in this case. Sound likes to travel through, well, it doesn't like, but it travels much faster through solids, slightly faster through liquids, and slower in gases. So fastest, you can call it the middle of the pack, and the slowest. And if it's nothing at all, it doesn't move at all. Light, on the other hand, travels fastest through nothing at all, travels a little bit more slowly when it goes into a gas like air, travels slower when it goes into a liquid, and it travels even slower or sometimes not at all through a solid. Whereas sound will travel very fast through a solid, a little bit less fast in the liquid, and slow in a gas compared to this. How many times faster? Just to give you an idea, I think in a solid, sound will travel, I think, something like 100 times faster than it would in a gas. But even sound traveling through a solid like steel, light would travel about 1,000,000 times faster than even that. So light's much faster than sound, but changing the medium of it, the more solid it is, the more dense the medium is, the faster sound will travel. Just less distance between these little particles. If you can imagine me pushing somebody in line, if they were closer to me, I'd be able to pass along the energy to them faster. Sorry. Okay, so the compression. The compression zones are these little parts where the molecules are crowded together. Now these could be air molecules, like in this tuning fork, or an instrument is compressing air molecules, the same thing with your vocal cords. Or it could be wood or metal. And if you think, like, what material would have the fastest, the best ability to compress? It's not about the material itself for the compressions, right? The energy that you put into it is going to provide for these molecules being compressed. Some might be more stretched out, so you can't give as much energy easily. It's like pushing up against air compared to pushing up against a solid table. You're going to be able to give more energy into the table than you are the air because it's just literally there. But in terms of the energy there, like if you're able to give energy, you could compress a lot more air when you're speaking loud. But if you want to compress more, say, of a solid material, you just have to hit it with more energy. The rarefaction would be the part that's spread out. Now, like I said, the more you compress, the more you're going to rarefact. It's a weird word. It's just basically think about it as the stretched out zones. Here's the compressed zones where it's getting pushed together. Here's where it's getting stretched from to get it to those compressions. So this is probably the closer diagram to what it would look like if you were to imagine that each of these is a air molecule, which doesn't exist, right? Air is actually a mix of many different molecules like nitrogen and carbon dioxide and oxygen. A speaker would be pushing back and forth on that air to provide a vibration. That vibration gives the energy. It's actually just pushing on air and then going back. You ever seen a picture of a speaker in slow-mo? It goes in and out, in and out, in and out. And as it does that, it pushes on these molecules, which push on these molecules, which push on these ones. And when you have louder sounds, it pushes more of them. If you have higher sounds, well, we're going to talk about that later, really. The properties come next video. That's generally how it's going to work. So they're always longitudinal, but a lot of people get confused because they're usually represented as transverse waves. It's hard to understand what this kind of wave would sound like or look like. It's hard to measure its its amplitude, its frequency. So most of the time when we represent sound waves, we represent them as transverse. I know that sounds confusing, but if you could imagine, like, it's just a mathematical transformation on a computer. They can do it instantly for you, right? If you can measure it this way, then and represent it this way, then it's not a big deal. And so they do that. And this is much easier to see. Oh yeah, the amplitude's higher right now. Whereas if you look in here, it's like, I don't know how many of these little molecules have been compressed right now to make the amplitude more. So there's mathematical transformations for it. We're not going to get into that because it is kind of advanced, but it's not impossible, that's for sure. So this is a transverse wave, but this is maybe what sound would look like. And I want you to think for a second, why would they look so different if they're both transverse waves? I know that little bar keeps coming at the bottom. It's annoying. I'm sorry. And the idea would be that the frequency is really messy. And it looks a lot more like there's multiple sound waves going at the same time, which is usually the case. There's actually multiple frequencies often involved in sound waves that overlap and interfere with each other to create what we see as these interference patterns on a transverse wave. So it's basically carrying different signals at the same time. When you're looking at a sound wave like this, you're actually seeing multiple sound waves overlapping. But that's what we hear anyway. That's why we show it that way. Okay, that was a very confusing end to the first day, first lesson really of sound. The next one we're going to get digging into the properties. Please do not forget to go on to the exit ticket now and go ahead and complete those 1, 2, 3, 4, 5, 6, 7 questions, I believe. All right, take care, and I'll see you in the next lesson.